factor, which is generally 1 for ideal and up until 2 for like completely unideal. Yeah, so it's basically a scale. K is Boltzmann's constant, which in any type of energy temperature relation, you'll normally find Boltzmann's constant, no matter where you are in electrical engineering. T is temperature in Kelvin, and then -1. So basically what this equation tells us is that if you have an exponent to 0, it'll be 1. So if your voltage is 0, exponent will draw to 1. -1 essentially equals 0, right? Which makes a lot of sense, right? Because if that diode doesn't have any voltage across it, it can't even have the forward voltage drop to have the conduction of the current and to drop our photovoltaic current for the VOC. Anyway, and diodes, we generally find a IV curve that looks like this, a sharp exponential rise at a certain voltage, right? And then almost like 0, just like leakage current flowing other than that, right? So super tiny current up until we reach 0.6 volts, and then we'll see an exponential curve in the current flow. All right, that's the one thing. All right, so if we go and look at a equation for a PV cell, we'll see it looks like this. It has an IV curve with a maximum power point that's around there, and it kind of looks like this, right? With your V and your I over here. Now, the interesting thing is that this kind of looks like a opposite of a diode curve. That's because it is. Because if you look at the diode curve, the circuit that we use to simulate it, right? Because if the voltage across these terminals gets high, it's terminal voltage because it is not connected to anything. So you'll lose the series resistance, right here, and it'll be VOC. So you'll have this higher voltage floating across your diode. So people, this essentially, I hope this helps, but this essentially describes the knee curve of your PV solar cells, right? It is basically the Shockley diode equation. Now, who is Shockley? Shockley is one of the 3 people that invented the transistor in the 40s. And solar cells have been simulated like this since the 50s. So if you do want VOC, you can basically take your basic equation, get VOC to the left, use your natural logarithms, to remove the exponent, and you can work out your VOC of each solar cell as well.